Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe a quantity called specific heat. So what we're looking at here, we've got two masses, and we're going to imagine that they're different materials, but the same mass. So this green mass here, we're going to say its mass is M, red mass, mass M. And these masses, we're going to assume at different temperatures. So we're going to have temperature of the green, temperature of the red mass. And what I'm going to assume for this example, the temperature of the red mass being quite a bit more than the temperature of green. Now, over on the lower left here, what I have is a graph of temperature against time. If there's no energy loss in the system, then the red mass temperature would stay constant. And we'd represent on the that on the graph maybe something like that. Green also constant. Right. Now what we're going to imagine is this. Imagine that we take this red mass and we put it in what's called thermal contact with the green mass. Now usually that does actually mean physical contact here. Right? So imagine these things are now in direct physical contact. But keep in mind the red mass is hotter than the green mass. So what's going to occur is that we're going to get energy transfer in this direction, right? And hopefully you've watched my previous videos here about heat and internal energy. So what's going to happen? This is a heat transfer. Heat usually is denoted with the letter Q. I don't really know why, but if I made up physics, I would represent it with the letter H. But H is actually typically reserved for another term called enthalpy. But anyway, so the red mass is very hot. Green mass relatively cool. So what's going to happen is we're going to get a heat transfer from red to green. And what's going to happen now is the temperature of the red is going to drop. The temperature of the green is going to come up. Now we're going to assume here that this happens kind of nice and slowly and there's no energy loss for the system. And again, very important to realize how we're defining our system. So our system now is inside of this surface here. Right? So we're going to imagine that we have only heat transfer from red to green, no heat loss out of the boundary or into the boundary. Right? So if that's the case, then what's going to happen is the temperature of the red will slowly go down, temperature of the green will go up. But depending on the materials, they're not going to necessarily meet halfway in between. The temperature will change until we have until both of these objects are at the same temperature. That's called the equilibrium temperature. And I'm just going to call that temperature, T for now. And that temperature could be closer to the red, could be closer to the green, depends on the materials. So this graph, I'm going to assume it ends up closer to the red. So that means that the green temperature will come up quite a bit until it hits the equilibrium temperature. Then the red will drop down until it hits this equilibrium temperature. And it's important to realize that the equilibrium temperature is the one I'm calling T here. So on this graph, that would be that temperature here. And I think what I'll do is go back and actually call that T final. All right, so T final on our graph is, right there. So the important thing to realize is that thermodynamically, these materials behave in a different way. Whatever this heat transfer is, maybe it's 10 joules, maybe it's 100 joules, maybe it's 1,000. I'm going to make up a number here. Let's say it's 100 joules. That 100 joules had much more effect on the green than it did on the red. And that's a reflection of what's called the specific heat of material. So I'm going to go ahead and define it. Specific heat. Most books represent specific heat with the letter C. Oops, I can write that a little better. And here's how it's defined. It's the heat required, or I'm just going to say heat needed, to raise 1 kilogram by 1 degree centigrade. So if we look at mathematically how that's defined, right, specific heat is defined as heat over mass degree centigrade, or I'll put delta T here. Right? It's heat per mass degree centigrade, or written more in equation form, C is equal to Q, because Q is the variable that typically represents heat, over m delta T. So your specific heat has units of joule per kilogram degrees centigrade. Now these are standard physics units. There's other units you can write specific heat in, but whatever units you're writing in, it has to be energy over mass times temperature change. This equation, if you look it up in your textbook here, is usually written Q equals mc delta T. Right? And what it's used for typically is for calculating temperature changes. You tell me a heat transfer and a mass, I would look up a specific heat for the material, and you can calculate a temperature change. I've got some examples written down. The specific heat of aluminum is around 900 joule per kilogram degrees centigrade. The specific heat of copper is around 386, same units. The specific heat of water is 4186, and again, same units, joule per kilogram degrees centigrade. Now, some things to notice about this. Water has a very, very high specific heat. Look at this. It's about 10, maybe it's about 11 times almost the specific heat of copper, and it's about 4.5 times the specific heat of aluminum. Now, what specific heat is a measure of is it's a measure of how difficult it is to change a system's temperature. Over here, if I go back to this red-green system here, the same heat transfer, in this example I was imagining 100 joules transferring from red to green. Well, that 100 joules brought the green temperature up quite a bit, so it had a drastic effect on green. But the red dropped very little. So in this example, the green would have a very low specific heat. The red has a very high specific heat. So materials that have a high specific heat, it's very difficult to budge their temperature. Materials with a low specific heat is very easy to budge their temperatures. Water has a very high specific heat, and that means it takes a lot of energy to heat up water. And this is why, I'll probably make a completely other video talking about some physical examples of this, but this is why lakes take such a long time to heat up in the spring, and they take a long time to cool off in the fall. Right? So the purpose of this video is just to describe what specific heat is. I'll go ahead and make other videos demonstrating how it's used in various problems. I hope that's enough for now. Everybody, hope you enjoyed it. Have a great day.